Hello everyone, welcome to the 10th session of quantum field theory. Today we're going to talk about mirror symmetries or discrete symmetries. In particular, three types: parity, time reversal, and charge conjugating. And parity is about a space inversion. So when we flip the coordinate in the space, but there is an effect on momentum. So space is connected to momentum here. And time reversal is time, but time affect momentum. I'm going to show you with P and a spin. So parity doesn't do anything with the spin, but time reversal also flip the direction of the spin, and it's because of anti-unitary nature of time reversal transformation. And then we have charge conjugating, which we change the type of the particle from the particle to antiparticle and from antiparticle to particle. So we don't change not the spin and not the momentum. So we start with the procedure, and the procedure then is similar for each of these transformation. I start with the parity transformation and try to understand the representation of the parity in the Dirac equation. And then time reversal and charge conjugating have a similar manner. And then at the end, I'm going to talk about CP violation. CP violation is something that we hear about it in the weak decay, in the concept of the weak force. And it is a symmetry breaking feature of one of the forces of the nature. The other forces of nature like QED and QCD, they don't have CP violation, but this is something about weak interaction. And I'm gonna have a very small introduction of what do we measure exactly for the CP violation and how can we experimentally observe the CP violation. But let's talk about parity, charge conjugating, and time reversal, and then when we combine them, we get a better idea. So first of all, let me talk about why these particular transformations are called discrete. It's because they are not continuous. And what does it mean that they are not continuous? It means that we cannot expand them. Like we cannot Taylor expand one particular transformation as a function of an infinitesimal parameter. So x mu, for example, goes to x mu plus epsilon mu, which epsilon was the infinitesimal parameters. Or I could say I have a transformation here that I can expand based on the exponential perturbation of some identity operator plus epsilon and epsilon squared and higher order terms. So this is why we call them continuous symmetry, like rotation, transformation in a space, translation in a space, and even boost. But for the discrete symmetry, this is not the case. It is kind of easy to see, because imagine that imagine the origin here, and then you have a vector here, p. Imagine I'm talking about momentum here, and then you flip it into minus p, and you kind of jump from here, point A, to point B, and there is no continuous connection between these 2 points. And there is another reason also that they're different fundamentally from continuous transformation, is that the squared of these transformations are equal to identity operator. So for example, imagine P is the operator that represents the parity transformation in the Dirac spinor space. So imagine P is representation of parity in spinor representation, or Dirac algebra. And P squared is equal to identity operator, because if you flip something 2 times, then it should go back to the original state. But if P squared is equal to identity operator, it means that there are 2 eigenvalues, and these eigenvalues are plus or minus 1. And when you have an operator which is plus or minus 1, if it's a Hermitian operator, if it satisfies certain condition of completeness, you can say that that operator can span your space into 2 individual subspace. So you can always say psi of x is broken into 2 components. Let me call this component plus component and then minus component of psi of x, which one of them is even parity, or I call it the one that responds plus 1 to the parity operator, and the other one is the odd parity, or something that has a minus sign as the eigenvalue. So in general, you can subdivide that space into individual spaces like right-handed and left-handed. So right-handed and left-handed are properties of chirality in particular. Okay, so I just wanted to say that why this transformation are basically different from the continuous transformation because their mathematical properties are different and their algebra is different. So if you square them, you're going to get identity. This is not the case, for example, for a small infinitesimal rotation and translation. Okay, let's start with parity and see how we get the parity as representation in the Dirac equation. Kind of makes Dirac, we want to find a representation that keep the Dirac equation invariant under the parity transformation. So we know what we're doing. We want to keep the Dirac equation invariant, so we want to find the properties of the parity operator. So we said in the Heisenberg picture, if you remember, there was Schrödinger picture and Heisenberg picture. In the Schrödinger picture, you apply the operators on the state, but in the Heisenberg picture, you apply the operators or transformation on the operators. And when you have an operator, you should sandwich a transformation. So imagine I have this psi of x, it's my quantum field, and my quantum field is the operator. So if you want to translate it, you need to have something like u dagger. And if u is unitary, it's a unitary operator. It can be also anti-unitary. So we see time reversal is anti-unitary. So imagine that parity is a unitary operator that I want to show it with p. So I'm going to use p dagger and p. And I want to see how the p operates on the creation and annihilation operators. So I want to see how a of, for example, imagine s and p. This is the annihilation term for a particle of type of a Dirac particle with a momentum p and a spin s under the parity transformation. So I want to see what this one is going to be. So this is my final goal. And my initial goal is to somehow start from an expectation. The expectation is the transformation of the field under that particular transformation. This is equal to gamma 0 psi of minus x and t. So this is where we start from. This is where we start, and this is where we end. Also, we want to find, for example, the behavior of b dagger of s and p under parity operator. So we want to find these two if we have the starting point. And if you look at the starting point, you might ask, why does it look like that? So there is two terms here. There is this gamma 0 and there is this psi. So this psi, only the space component of it is flipped. And it makes sense why, because we're talking about parity. We want to distinguish a space from time. It's like a mirror of a space, not the mirror of time. So, it's just a pure space mirror. But this gamma 0 might be ambiguous. The reason that we have a gamma 0 is the following algebra. I mean, it is like bibbidi bobbidi boo is from future, but if you apply gamma 0 to u of s and p, so this is the free solutions of the Dirac equation, this flips the direction of the momentum, and only the direction of the momentum, and that's why these gamma zeros are interesting. So if you also apply gamma 0 to v of s and p, that would be v s of minus p. And in particular here, we want to do that. We want to flip the space coordinate. So maybe I have to clarify here. So when you are applying parity, your coordinate, not your observables, like your quantum field, only your coordinate goes to the inverse of themselves. So x goes to minus x and p goes to minus p. And they are both coordinates, they're both coordinates and they're actually Fourier partners of each other. So now the question is, how does the field transform? And this is the expectation that we have, and that gamma 0 is specifically related to the Dirac algebra. We put that gamma 0 in order also to keep the Dirac equation invariant, and also it does that trick that it only flips the coordinate of the momentum, and this is something we want to do. But something interesting is that if you just pay attention to the coordinate flipping here, so if x goes to minus x and p goes to minus p, then the angular momentum is invariant. So j, which is x times p, is invariant under flipping the coordinates, and it's obvious. So it's like physics is invariant under parity, and angular momentum is kind of invariant under parity, and maybe it gives you an intuitive idea why the spin is not flipped under parity. But in time reversal, it does, just to make sure that we understand the difference between parity and time reversal. So, okay, so we have this equation, and we want to see how to get to the effect of parity operators on the creation and annihilation operator. So let me start with expectation. So when I'm starting with expectation, I just have to kind of use the expansion or using the quantization of the Dirac operator on the creation and annihilation operator, and then find how to make that comparison 2 by 2. So let me say that p psi of x and t, p dagger, is equal to the integral of d3p 2 pi 3 1 over 2 ep sum over a spin Then we have p dagger, and then we have this a s of p, and let me write it down like u s of p, and then a s of p. And a is an operator here, and u is kind of a spinner. It's a spinner component. And you have this exponential term outside, and then you have plus p dagger, v s of p, b dagger of sp, and then I have the exponential term, exponential I plus p dot x. Okay, so now I have that. And what is on the right side? On the right side, we have gamma 0 psi of minus xt. So again, I'm going to use the quantization of the Dirac field, but I'm going to use another coordinate, p prime, because we can see it's an integral, and we should use actually different variable name. So dp prime. I apologize if I repeat everything so many times, because just repeating is a good way to remember. So I have this, now I don't have this p operator here, so I have this gamma 0 here. So I have this gamma 0 u s of p. So maybe I'm actually using not a consistent notation, but let me use s and p in that way. But maybe I used a different notation previously, but it's the same meaning. It's just how I write it. And then I have a of sp, and then exponential of e minus p dot. So here, instead of x, if you compare it to here, to this x here, I should use minus x here, because I'm flipping this coordinate. And then I have the next term here, gamma 0 v s of p, b dagger s of p, exponential of plus I p, now again, minus x. Now, if I want to put, I'm sorry, I forgot all the prime, actually, p prime. So all of these are p prime, forgive me. So just, so now these two should be equal to each other. And then you have to make a 2 by 2 comparison between these terms. So this term here, for example, with this term here, and this term here with this term here. But let me just go, for example, to the red term here. So how can I exactly say that they are equal? I have to do a kind of trick, because I basically want to find the effect of this p and p dagger on this particular operator. But down here, I have another term. The term is this u. So I have to deal with this u, and then I have to deal with this exponential. So if I make these exponential terms to be exactly similar to each other, and this u term to be exactly similar to each other, then I can put the rest of them equal to each other. That's the worst way that physicists try to do math operation, but it's intuitive. So the only thing that I have to do is to again flip one of these coordinates, so these two exponential terms are equal. So instead of now p prime, I'm going to use something p tilde, and this p tilde is minus p prime. So I have to say p tilde is minus p prime. So now my terms are going to be like this. So on top we have p usp asp p dagger exponential of e ip dot x. This is on top. This is equal to gamma 0 usp prime. So now let me rewrite it based on p tilde. So now us of p prime is going to be us of minus p tilde. This one is going to be as of minus p tilde, then exponential of ip dot x. On top, I can take this u out because it's a spinor component. So this is going to be us of p. So now, if you look, this omega is this gamma 0, sorry. This gamma 0 is the one that does the trick. So this is going to be us of p tilde, because it flips the coordinate. So I'm going to have u, and I have the integral here. So don't forget that we have integral here, but with different variable name. So I have us of p dagger as of p exponential of ip dot x is equal to s of p tilde as of minus p tilde exponential of e minus p tilde dot x. And there is integral here. this one over dp, this one over dp tilde. So therefore you can conclude that p dagger of a s of p is equal to a s of minus p. Now I can kind of say that p tilde and p are the same variable because they're inside of the integral, two different integrals. So if I wanted to say the terms in the integral, they can satisfy. The terms inside of the integral, they satisfy this equation here. So the same logic also applies to b dagger of s p. P dagger, this is equal to b dagger s of minus p. So parity, what parity does is to flip the annihilation of the particle with momentum p to the annihilation of the particle with the momentum minus p with the same spin, and also creation of the antiparticle with momentum p to the creation of the antiparticle with momentum minus p but with the same spin. Okay, now let me write down the transformation for both psi of x and psi bar of x. So for psi of x, this is going to be and for psi bar, we have the dagger of those operators. Bs, p, b dagger, sorry, bs minus p. So this is how parity operator transforms the creation and annihilation operators. Something else that we can prove is that how parity change the handedness of the particle. So we previously talked about how Dirac equation is basically two independent SU2 representation that they act independently. So each of them are basically transformed separately by SU2 transformation, and we call them right-handed or left-handed. But let's analyze it more carefully. The handedness is basically the eigenvalue of gamma 5 operator. So this gamma 5 operator is I, gamma 0, gamma 1, gamma 2, gamma 3. There is no gamma 4. And this gamma 5 is interesting in a way that you can define two operators here. So one of them is, let's say, 1 minus gamma 5 divided by 2, and the other one is 1 plus gamma 5 divided by 2. And the reason they're called P is because they are projection operator. And PL plus PR is identity operator. So therefore we have completeness. So PL and PR can break psi into two orthogonal component. So I can say psi of L, or left-handed component of psi, is PL on psi. And psi R is equal to PR psi. So this is how we project them. And you can always say psi is equal to psi R plus psi L. So that's how we say a fermion is basically have two independent subspace that each of them transform with an individual SU2. So now we want to prove that if we apply parity transformation, how right-handed and left-handed fermions transform to each other. Oh, by the way, I have to say that psi R psi L dagger is equal to 0, or psi R dagger psi L is also equal to 0. That means that they are orthogonal. They are separated. They are independent. They're two different things. Okay, now let's go back to gamma 5. So gamma 5 was this I, gamma 0, gamma 1, gamma 2, gamma 3. And so if we have gamma 5 on psi left-handed, means gamma 5 on 1 minus gamma 5 divided by 2 on psi. And let's say gamma 5 on right hand is equal to gamma 5 1 plus gamma 5 divided by 2 of psi. And you can simply show that this is equal to minus psi L, and this is equal to plus psi R. Why is it the case? because we can basically rewrite this operator as gamma 5 plus gamma 5 squared divided by 2. And, gamma 5 squared is 1. So I have 1 plus gamma 5 again divided by 2. So I just basically have psi r again. But if I have gamma 5, 1 minus gamma 5 divided by 2, I have gamma 5 minus gamma 5 squared divided by 2. I hope that you're not making a mistake between this 5 and this 2. This is a power here. And this gamma 5 is index. So this is equal to minus 1 minus gamma 5 divided by 2. So that's how psi of L, there is a minus sign. So this is odd parity, we call it, and this is even parity. So each fermion has 2 individual components which they have opposite parity. And now we can prove that if we apply the parity on psi of L, let's say, I'm applying parity on 1 minus gamma 5 divided by 2 of psi. And then I have what? I can take 1 over 2 out and just basically say I have P psi P dagger minus P gamma 5 psi P dagger. And now I can say, that this term here. So I'm going to go to this term. P gamma 5 psi P dagger. This is equal to P gamma 5 P dagger P psi P dagger. And I want to show that this term here is equal to P, this term. P gamma 5 P dagger is equal to minus gamma 5. To prove this, I need to go back to, again, Dirac equation. Now I'm requiring that this equation is invariant under parity. So basically, psi prime, which is equal to P psi P dagger, should also satisfy Dirac equation. Also, we are performing parity here. So we're also flipping the coordinates. So x goes to minus x. And you can say d mu goes to minus d mu. Oh, by the way, we have to separate the space and time. So x goes to minus x, but t goes to t. And d0, the derivative with respect to time, doesn't change, but the space derivative is going to be flipped. So at the end of the day, if you apply all of this transformation together, you have to require that the gamma matrix and the parity operator satisfy the following equations. If mu is equal to 1, 2, and 3, this is equal to minus gamma mu. And if mu is equal to 0, that's gamma 0. And you see why am I making such a choice. So this is something that it should satisfy. And I can basically use this term. And I can use this term to show that P gamma 5 P dagger is equal to P I gamma 0 gamma 1 gamma 2 gamma 3 P dagger, and this is equal to I P gamma 0 P dagger P gamma 1 P dagger P gamma 2 P dagger P gamma 3 P dagger. Sorry, it is very small, but there is no sum in between them. It's just there is only multiplication, and from this, the only term that doesn't change is this gamma 0. So we're gonna have P. So that term is going to be only gamma 0. The other terms are going to be all flipped. So 2 of them are going to go out and there is 1. So this is equal to gamma minus 5. So that's how P gamma 5 P dagger is equal to minus gamma 5. So now I can basically use it here. I was saying that psi of L, you have P and P dagger, is equal to P 1 minus gamma 5 psi P dagger. That is equal to 1 over 2 P psi P dagger minus P gamma 5 psi p dagger. This is going to be p gamma 5 p dagger p psi p dagger. This is equal to then p psi p dagger minus, now this gamma 5 is going to be flipped, minus gamma 5. This is going to be plus gamma 5 p psi p dagger. And then you can say 1 over 2. I can take now p psi p dagger, factorize it, and say 1 plus gamma 5. And this is equal to 1 over 2, 1 plus gamma 5 p psi p dagger. And p psi p dagger is equal to gamma 0 psi of minus xt. And we also have this operator behind it. So I have 1 plus gamma 5 divided by 2. So I'm going to have 1 plus gamma 5 divided by 2 gamma 0 psi of minus x and t. And I can basically commute these two gamma here, gamma 0 and gamma 5, because gamma 5 is made of gamma 0. So I can say gamma 0, 1 plus gamma 5 divided by 2 psi of minus x and t. And I'm going to name this phrase here psi r of minus x and t. So p psi l p dagger is equal to gamma 0 psi r minus x and t. Similar logic for the right hand. So you can see how parity is a transformation, and how did we find the representation of the parity in the spinor representation of the Dirac operator. So this is what we know here. And also where we start. Okay, now let's go to the other transformations. Okay, now we know how, for example, right-handed and left-handedness are converted to each other. I want to say that chirality doesn't change with boost. So chirality does not change with boost. What does it mean? It means if I take the frame of reference, which I have the momentum p, and I take it to a frame of reference which has the momentum p prime, gamma 5 is the same gamma 5. It's just algebra. So gamma 5 is not something that it is a function of boost. So chirality is intrinsic. Chirality is something intrinsic. It's not changed by the frame of the reference. However, we have this helicity. Helicity is equal to s dot p divided by the direction of p, which projects spin. I mean, spin in three-dimensional spin, and the momentum. And therefore, also this h also have the eigenvalues of plus or minus 1. So it's still similar to chirality. It spans particles into two groups, one with plus 1 helicity and the other one with minus 1 helicity. But here h is a function of boost because there is a p term here. So this goes up and down with boost. So therefore helicity is not the same as chirality. Now exactly when helicity and chirality are equal, when we have a massless particle. So here, I mean, you can have a massless fermion. For example, you can have massless fermion, which is the Dirac equation basically with mass equal to 0. So in this particular manner, chirality and helicity are basically the same. Chirality, we know it's right-handed and left-handed, but why helicity is the same as chirality? Because for a massless particle, we cannot basically change the frame of reference. We can never flip the momentum. We can never, if you have a photon, if you have a massless particle with momentum p, or a massless particle, you can never take it to the momentum minus p. You can never stop it. So basically, in a massless fermion, helicity becomes unchangeable because the frame of the reference cannot be changed. So the helicity is intrinsic if helicity doesn't change with boost, then the helicity is intrinsic. So therefore, helicity and chirality are the same. For the case of the massless particle, and here massless particle are basically fermions, massless fermions. And for the case of massive particle, helicity and chirality are not the same. So you can change the helicity. So you can change, a particle with helicity 1 plus 1 to a particle with helicity minus 1. But not essentially the same thing that you can take a right-handed fermion to the left-handed fermion. There's not a one-by-one relationship here between helicity and chirality when you are changing the frame of reference and taking something from plus 1 helicity to minus 1 helicity. So I hope that the difference between helicity and chirality is now clear. So now the similar procedure is applied for the other transformations. For example, time symmetry. There is a little bit of trick here on time symmetry and charge conjugating. For example, in the time symmetry, which I'm now showing with T, I expect this. So T acts on psi of x. And, my expectation is set to be gamma 1, gamma 3 psi of x and minus t. And, we have similar reason why did we choose gamma 1, gamma 3, because so if I apply gamma 1, gamma 3 on u s of p, that would give me u of minus s of p. And if I apply gamma 1, gamma 3 to v of s of p, this gives me v of minus sp. But the conclusion that I make regarding to the creation and annihilation operator is this: as of p under time reversal is going to be a of minus s minus p. So here we have to use them and change the exponential terms as we did for parity. And t for b dagger of sp, t dagger is equal to b dagger of minus s minus p. And similar for psi bar. So for psi bar is t a dagger sp, t dagger is equal to a dagger minus s minus p, t b dagger, b s p is equal to b minus a minus b. Okay, just have to mention that t is anti-unitary. T is anti-unitary. What does it mean? For a unitary operator, we have expression like this. So imagine I have some psi and phi. So the unitary operator preserves the inner product of two states. So we have, psi dagger, your u dagger psi and u phi. So this is called unitary if we have such a property. But imagine if you have something like this: t dagger psi t phi. Imagine that I have a star here. So this star is basically doing a complex conjugating. And the complex conjugating means that if we have time reversal operator act on I, or the complex number, this is equal to minus I. So this is what we call it anti-unitary. The unitary operator should be like this. P, for example, parity should be equal to plus I. So you see there is a difference between time and parity. And again, this difference is because of the inner mechanism of the algebra in the Dirac equation. And let's go to the last one, which is the charge conjugating. In the charge conjugating, we only flip the type of the particle to antiparticle, and vice versa. So expectation is C. This is what I show charge conjugating. Act on psi of x and t, C dagger, is equal to, imagine, is equal to I gamma 2 gamma 0 psi bar transpose x and t. And the reason for these gamma matrices is because they flip the Dirac answer into each other, but in the opposite way. So if you apply I gamma 2 gamma 0 to u, s and p, this gives you v, s and p. And if I apply I, gamma 2, gamma 0 to V, S, and P, this gives you U, S, and P. So therefore, we can define the effect of this charge conjugating operator on the creation and annihilation operator. So if you have C, and if you have A, S, and P, C dagger, this is equal to B of SP, same type, annihilation, annihilation. But in this one, you annihilate A, or psi part of psi particle, and in this one you annihilate B, not A. And if you have C of B dagger SP, C dagger, this is equal to this is equal to A dagger of SP. So this is how, and for the case of psi bar, C, A dagger, SP, C dagger is equal to B dagger, SP, and C on B, SP is equal to A, SP. So this is how you can cover all of them. So now this was about charge conjugating. And now let's talk about CP violation. So CP violation. So we have this separated transformation P, T, and C. And let's say Dirac equation respects parity, respects time symmetry, respects charge conjugating. And you have QED, for example. QED is technically the Dirac equation plus electrodynamic, or A mu, or electromagnetic field. This one also respects all of these three. The other one is the Dirac equation plus, let me write it with another color, QCD, or the same type of field. You call them Yang-Mills field, but you add some index here. And this also individually respects these symmetries. So any combination of them, CP, TPC, is also well respected. There is one exception, which is weak force. So weak force is a little bit different. And it's interesting that we first realize how weak is the weak force, and then we try to figure out or explain why the weak force is so weak. And I think it's always weird. You always have to explain why the weak force is so weak and why significantly the weak force is different from QED and QCD. Because if you look at QED and QCD, there is a mathematical connection between these two. Both of them respect a symmetry, but in different dimensions. And then the weak force is also similar, but there is a fundamental difference between the weak force and the other force. And that's how the flavor is carried by the weak force, or is changed by weak force. So weak force has a term that violates certain symmetries, and it is the flavor changing. We lose the flavor in the weak force. So if you think about the quark, you have up, down, a strain, charm, bottom, and top, and then the weak decays take you from one of the massive state to the lighter state, but it is not a symmetric decays, because it usually decays into the lower and lower mass, but on the other hand, you cannot decay into higher and higher mass. Anyway, the weak force has a term, like for example in Lagrangian, it's called Yukawa term, that I have the left-handed quark, and then I have a right-handed quark. Imagine I have a Dirac sandwich like Lagrangian, and then in between I have some stuff that I call them a scalar field, which is coupled to a matrix, which is a Yukawa matrix. And these matrices are basically encoding how the flavors are interconnected to each other. You can mathematically define a term, you call it A of CP, which is the cross-section of the processes, the decays that you observe in nature, minus the cross-section of the CP conjugate of that process. So if there is a process, there is a decay, you try to see what is the CP conjugate of that process, and then you calculate this variable on the denominator you have a plus. So same terms, but the plus. So what happens when the process is exactly having a counterpartner that is a CP conjugated process? If both of them are equal, then this is equal to 0. So there is no CP violation. But if it is non-zero, then that means CP violation. And these processes are observed in laboratories. Certain decays, for example, long-lived kaon decays into pi plus and pi minus. K0 decays to pi plus and pi minus. In 1964, James Cronin and Wolfich measured the discrepancy in the decays of the kaon. Another one is the B meson, or the mesons that are made out of the bottom quark. So they have a certain decay channel. They decay into a J psi. J psi is charmonium, Ks, or you have B0 decay into J psi, or a phi, or you have B0 decays into pi plus and pi minus. So these ones were measured in a SLAC in early 2000. There were more. For example, recently we measured baryons, bottom baryons decays into proton and pion, and they're also antiparticle decays into antiproton and pi plus. And in 2019, LHCb measured these certain decays to violate CP conjugation. So for some reason, the weak force does not respect CP symmetry. Okay, there we are. So I think we covered the discrete symmetries, and we are done with the free Dirac field. Up to this point, we were only discussing free fields, Klein, Gordon, and Dirac, and in the next session, we will start interaction picture. In the interaction picture, we will see how different fields, they see each other, they're coupled to each other, and they interact with each other, and how these interactions are basically elementary particle interactions, how two fermions see each other by use of a photon or a gluon or something that we call it a gauge field. So we can go forward and see how these concepts are all going to merge in a very beautiful picture that we can calculate the cross section of the processes and Feynman diagrams and many other exciting things. So thank you so much for watching this episode, and see you on the next episode.